Welcome to Speaker Night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton, and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope at the David Dunlap Observatory. Together with Shaheen Dashkian, our outreach coordinator, I'm delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's lecture. If you haven't already, please take a moment to say hi in the YouTube chat and tell us where you are joining us from. This helps us make sure that our technology is working properly. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to Canada's largest optical telescope. While we miss welcoming guests to the DDO facility, we are happy to bring you virtual programming this summer instead. We would like to start by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge that this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. It is my pleasure to introduce our speaker for tonight, Vidhya Ganesh Rangarajan. Vidhya is a PhD candidate in the Geology and Planetary Science at the Institute for Earth and Space Exploration and the Department of Earth Sciences at the University of Western Ontario. He is also a student science team member of the Color and Stereo Surface Imaging System camera on the ExoMars Trace Gas Orbiter, and helps occasionally in science and operations planning for the instrument. He holds a bachelor's degree in civil engineering and a master's in remote sensing, and has previously worked as a research fellow at the Indian Institute of Technology, Guwahati, and later as a project scientist at the Indian Institute of Technology, Kanpur, on projects with the extended Mangalyaan and Chandrayaan science teams to help characterize Martian and lunar surfaces, respectively, from remote sensing spectroscopy. Tonight, Vidhya will be speaking about Earth's next door planetary neighbor, Mars. His talk grows out of his own studies of the active surface processes that continue to shape the planet. If you have questions for our speaker, please post them in the YouTube chat. Vidhya will have time to take your questions at the end of his talk. Please join me now in welcoming Vidhya.
Thanks so very much, Denise, for that lovely introduction. Hello and good evening, everyone. It's a great pleasure to be here and talk about a topic that has been emerging as a very important field in the past decade for Martian studies. We all know Mars has been a huge planet of interest for exploration, and it's often referred to as a planet that may have hosted life billions of years ago. But at present, our ideology of Mars is something like a dry and deserted state planet, almost dead to a certain extent. Now, indeed, geological activity has ceased. There's no volcanism, there's no tectonics going on there, but there are still a lot of processes that take place at the surface and also at the near atmosphere level that still render the planet very, very active. Sometimes it is geomorphologically even more active as compared to the Earth. Now, over the next 40 to 50 minutes, I'll attempt to illustrate how active actually Mars is. What are the different types of changes you see? What's actually causing them, and why learning more about present-day activity is so very crucial to understanding more about the planet itself. Now, before we delve too much into the activity aspect of Mars, let's get some basic idea of how different or similar Mars is as compared to the Earth. And we all know Mars is roughly about half the size of the Earth and probably half the distance greater from the Sun as compared to the Earth. The day lengths are pretty much similar, except that Mars has an extra 40 minutes in its Martian solar day. Now, We know that Mars is farther away from the sun as compared to the Earth. So indeed, the year length of Mars is roughly about 687 Earth days, which is greater than that of the Earth, roughly twice. Mars also has an axial tilt of about 25 degrees, very similar to the Earth. But then we need to understand that this is the current axial tilt of Mars. The obliquity of Mars actually varies from 0 to 45 degrees in a period of about 125,000 years. And drastic changes are seen in time spans of 5 million years or so. This is essentially because Mars does not have a very solid planet-moon system as compared to the Earth-Moon system, wherein it's tidally locked to its satellite. And that causes the planet to sort of wobble around its vertical axis too much. And that induces great changes in seasons and other surface processes that occur on the surface. Now, we know that the atmosphere is completely different as compared to the Earth. While the Earth's atmosphere is nitrogen dominant, Mars's atmosphere is CO2 dominant, with almost 95% of CO2. Mars does have water vapor and a bit of nitrogen in its atmosphere, but they're all in very trace amounts. Now, although Mars's average surface temperature is very, very low, about minus 63 degrees Celsius, the key important aspect which actually governs most of the active surface processes on Mars is its much, much lower average atmospheric pressure, which is just about 600 pascals as compared to Earth's 101 kilopascals. Now, these lower surface pressures, what they basically do is that they reduce the freezing point of gases so much. For example, if you have a glass of water, water freezes at 273 Kelvin on Earth. But because of the lower atmospheric pressure, water would indeed freeze at 190 Kelvin on Mars instead of 273 Kelvin. Similarly, CO2 freezes at 130 to 150 Kelvin as compared to 200 Kelvin on Earth. So this hugely impacts the way surface processes take place on Mars. Now, Mars has been explored since generations now. This is one of the first global maps that was prepared by Giovanni Schiaparelli in the late 1800s. Although we've gotten much better with characterizing the geology of the surface, especially with the remote sensing era, when we had the Viking and the Mariner orbiters in the 1900s. But until the Mars Global Surveyor actually came into orbit, we never knew of Mars being active at all. We'd almost stamped Mars as a cold, dead planet already by then. Now, most of the features that were identified pre-Mars Global Surveyor era were just impact craters, volcanic structures. We did identify large canyons and channel systems running all across the planet, but all these were indicative that Mars did have some sort of active feature in the past, not the present. The only active feature that we could see, even from telescopes and earlier satellite data, was that Mars did have polar caps, and they look so much like the ones that we have on Earth. Now, the only difference between the Martian poles and Earth's poles is that, yes, Martian poles do have water ice, but they also have something called as CO2 ice or dry ice that's being deposited on the northern pole and the southern pole. These are two Hubble Space Telescope images that were taken. One was taken in March 1997, and the other one was taken in August 2003. Now, one thing to note again is that because of the very low atmospheric pressure that Mars has, because of its very thin atmosphere, the triple point conditions for both H2 and CO2 are never met on Mars. What this basically means is that both H2 and CO2 cannot exist in all three states at the same time. So very majorly, they cannot exist in liquid state. One might question, hey, both these poles look very similar in color and texture as compared to the Earth's poles, right? How did we know that there is CO2 ice as well? The answer is we actually didn't know until we had some IR data from the surface. The first IR data I think we had was from the Omega instrument on the Mars Express, which conclusively proved that there is CO2 frost that's getting deposited at the poles. And much later, this was conclusively provided by the XRISM instrument on the Mars Reconnaissance Orbiter. Now, most of the activity on Mars is either season-centric or at least dependent on which season Mars is in. So to better understand what's actually going on the surface, we need to understand the various seasons on Mars as well. Now, as I mentioned before, a Mars year is nearly twice as long as an Earth year, roughly about 687 days, Earth days. Now, how we define each period of a Martian year is that we use a term called as solar longitude, or L sub S. Basically, it depends on, it's just an indicator of where Mars is in its orbit as it revolves around the sun. It is it's defined in such a way that a 0 degree L sub S corresponds to the beginning of northern spring, 90 corresponds to the beginning of northern summer, 180 corresponds to the beginning of northern autumn, and 270 corresponds to the beginning of northern winter, and vice versa for the southern hemisphere. Now, one interesting thing you might note from this pictograph that's there on the right side of the screen is that the orbit is not circular at all. In fact, Mars has a very eccentric orbit, almost second, I think it's the second most eccentric orbit as compared to in the entire solar system. I think only Mercury has another eccentric orbit here. And what this does with these seasons is that the winters in the southern hemisphere are insanely long as compared to the winters in the northern hemisphere. And vice versa, the summers in the southern hemisphere are very short as compared to summers in the northern hemisphere. And this hugely impacts the surface temperature that's experienced by various latitudes on Mars. This is a nice GIF that I put together from running the Mars climate database models. This is basically a graph that shows how the surface temperature varies at various latitudes as a function of the solar longitude. One key thing to note here is that in the northern pole, we do experience temperatures greater than the freezing point for both CO2 and H2O. But this is not the case in the southern hemisphere at all. Near the south pole, there's always temperatures lesser than or in between the freezing points of CO2 and H2O, always present near the southern pole. This causes not all of the frost that's being deposited during the local winter to sublimate completely. And that's why we have something called as a residual south polar cap that's seen on the right side of this GIF here. This is a nice animation that was prepared based off on IR observations from the TESS and the MCS instruments on the Mars Global Surveyor. One fun fact to note is that during deposition phase, almost 25 to 30% of the atmosphere or the CO2 present in the atmosphere is completely deposited at the poles. Now we know that both H2O and CO2 is present at the poles, but how is it actually distributed? Is it really the same between the northern and the southern poles? Apparently it's not. In the northern pole, now H2O ice is common in both the poles, but then the north cap actually consists of layered water ice and dust sort of layers there, which we call as the north polar layered deposits. And then every season during the local fall and winter, a seasonal layer of CO2 frost gets deposited on it, and then it sublimates in the local summer. It sublimates completely in the local summer for the northern hemisphere, but it does not for the southern hemisphere. This is because, again, the southern hemisphere has such a long winter, so there's a lot of CO2 getting deposited on the pole, but then because it has such a short summer, not all of it gets sublimated away. The colder southern cap also again has H2O ice, but it's predominantly dominated by CO2 ice. This is because the southern hemisphere experiences much, much colder temperatures because it's much farther away from the sun. So the temperatures are almost always below the freezing point of CO2. So a lot of CO2 gets deposited there. Now, because the southern hemisphere is also slightly higher in elevation as compared to the northern hemisphere, it also experiences a much lower atmospheric pressure. So that doesn't really help because it lowers the freezing point further. And then we see a lot of cool, weird polar processes that occur near the South Pole. And this is much more common as compared to the North Pole, as you might see in later slides. Now, okay, one might think the Mars poles, okay, the ice in the Mars poles is probably expanding, shrinking. Why should we actually study this? In fact, the study of active processes goes beyond an accumulation of just listing number of surface changes and just quantifying the rates or effects that they have on the surface. We know that there is a very close relationship between what processes that occur on the surface and the lower atmosphere. So the fundamental objective for us is to understand what processes are being driven by the atmosphere, atmospheric variables there. This will help us improve interpretation of various features that are left behind by these processes on the Martian surface. Now, many of these processes were not predicted at all before their effects were first observed. For example, seasonal CO2 frost-driven phenomena. We never knew of it until we could conclusively prove that CO2 frost existed on the surface itself. And that was just the beginning of this millennium. So better understanding current processes will help us search for much more unanticipated processes that may be occurring that we still don't or can't comprehend yet. Now, present-day Martian processes, some of them do not have terrestrial analogs at all, as you might recognize towards the end of the presentation. Now, however, these might have left their imprints in the ancient rock record that's already present on the Martian surface. So without a clear understanding of what's going on the surface right now, we may be misinterpreting all these records completely. And so we can't get a clear picture of what would have caused these features to form in the first place. Now, one of the most important aspects why we do study current activity on Mars is that to provide a safe pathway for future robotic and human exploration, not just by finding out which locations are good for in situ resources in case we have a future landing mission, or maybe sites for looking past habitability, or maybe looking at good landing sites for future exploration missions, but also safety aspect of astronauts when they actually land, when we do have landed missions in the future. Now, I'll show you one really good example to illustrate this much more better. Now, these are two high-rise images taken of the Phoenix lander, which actually landed in May 2008 in Utopia Planitia. It is sort of like a periglacial region in the northern hemisphere of Mars. Now, at the time Phoenix was designed, we didn't know of CO2 processes to be occurring, or we didn't know the strength of CO2 processes that was occurring on the surface. So Phoenix was never designed to survive the harsh cold winter on Mars. So if you see keenly the 2008 high-rise image that's there here, we do see two bright blue spots on either side of the landing system that corresponds to the spacecraft's clean circular solar panels. An artist's impression of the Phoenix lander is actually shown in the right side of the screen. These are the two clean circular panels that Phoenix was fitted with so that it gains power and runs its instruments there. Now, one thing to note is that all these images are taken at a certain inclination angle from the sun, right? So almost always, these instruments cast a shadow on the surface. Now, in the 2008 image, we do see the shadow on both these sides for the solar panels. But however, if you look at the 2010 image a bit more keenly, we see a dark shadow on the eastern portion of the entire assembly. That could be the lander body and the eastern solar panel, but there's absolutely no shadow in the western solar panel at all. So what basically happened was, in the local winter in 2009, CO2 ice basically deposited on the western solar panel. It built up so much that it potentially bent or broke the entire western solar panel. This gives us an idea that if seasonal frost has enough capability to destroy a robotic equipment that's there on the surface, it surely does have enough capability to affect landform evolution on the surface, and all that we see on the Martian surface today. And that makes it even more critical for us to better understand what's actually going on the surface so that we can design future missions to avoid or to withstand such processes in the future. Now, for all active processes on Mars, there are three major environmental drivers that almost guide every surface phenomena. Frost and ice, definitely, because Mars is definitely a cold planet. This frost or ice can be both atmosphere sourced, or it could be buried ice as well that could have been deposited at much higher obliquity periods. The other agents that guide these phenomena are gravity and wind, because gravity, it is a terrestrial planet after all, so it does have gravity. And because Mars moves or wobbles around its own axis, it does have wind as well. One thing to note is that frost ice phenomena are mostly found in the mid to high latitude regions of Mars, and so is the gravity related surface processes as well. However, most of the mid to lower latitude or equatorial latitude landforms are mainly driven by wind. This a list of all major active surface processes that we see on the Martian surface. Now, over the next series of slides, what I'll basically do is I'll show you high-resolution images that the HiRISE and Cassis cameras have actually been acquiring of each of these features so that we can try to understand what exactly they are and how we think they might have formed. Let's first start with the processes in the poles, which are dominated by frost, and then slowly move down towards the equator where wind basically governs the major environmental changes that we see on the surface today. Now, as I mentioned before, because the southern pole has so much of CO2 deposition, that's where we find a lot of weird processes that are going on as compared to the northern pole. Now, there are two such processes that are almost solely seen only in the southern hemisphere, at least a greater density of them is seen in the southern hemisphere. One of them is something we call as a Swiss cheese terrain, simply because these pits look somewhat like Swiss cheese, the holes in the Swiss cheese. Now, these are essentially small pits that are formed in the South Polar ice cap, especially when CO2 frost sublimates during the local spring. Now, basically what happens is that the sublimation is preferred on the walls of these round depression instead of the floor. This is because these walls have a certain slope, right? So they receive more intense sunlight as compared to the floors, which are relatively much more flatter. So what basically happens is these walls essentially get eroded, and because of that, the pit size keeps on increasing every year. Almost the average rate of increase that has been reported from remote sensing images has been roughly about 1 to 3 meters per year. So this is very much an active process. As you can see, this is a nice comparison of two Mars observer camera images that was taken by the Mars Global Surveyor spacecraft between 1999 and 2001. So this, again, because it's a CO2 frost-driven phenomena, we don't have any analog on Earth because CO2 frost doesn't get deposited on Earth. Yet another process that actually is solely seen in the South Pole is these formation of raniforms, or something we call as polar spiders, because they look so much similar. Now, these are essentially dendritic structures that are again thought to be formed by sublimation of dry ice in the local spring. Now, these are essentially found more near the South Pole as compared to the North Pole because the South Pole is much more rich in sand. And that's what scientists think starts the entire carving process of all these dendritic structures. Now, basically what happens is that during the local winters, a translucent layer of CO2 frost gets deposited there. And then when the local spring comes up, sunlight is always incident on this area, right? The sunlight basically penetrates this translucent layer and it heats up the ground underneath. Now, what this basically happens is that this heating causes the ice to sublimate from its base instead of the translucent ice cap. So we have a translucent ice cap, we have all these volatile materials that are present here. And because of these volatile materials, it increases the pressure inside this sort of cap that's formed here. And that causes cracks to form in the form of these dendritic structures in the translucent CO2 ice layer. Now, and all these volatile materials that has been accumulated between the translucent CO2 cap and the lower sort of ice deposition there, everything just gushes out of all these cracks, and it forms water ice clouds as these spider structures keep on getting bigger and bigger. Now, once all these volatiles are almost released to the lower atmosphere, it only leaves behind this zigzag sort of spider-leg pattern that is visible on the Martian surface today. Now, yet again, because this process is completely governed by CO2 sublimation, we absolutely don't have any analogs on Earth, which makes it so much more difficult for us to at least pinpoint to, okay, this is what is actually causing this change to occur on the surface. All this is, we're trying to model what could be the case based off of remote sensing observations, maybe compositional data, IR data, thermal data, and radar observations from these locations. Now, as I told you, drastic changes are obviously seen in the southern hemisphere, but that doesn't mean there is absolutely no change in the northern hemisphere. CO2 frosting and defrosting also takes place in the northern hemisphere, right? And what it basically does is that it forms these dark spots, which are formed as a result of these CO2 jets getting released when sublimation occurs. Now, this sort of activity is found in both southern and the northern hemisphere. This is a series of simulated CASIS images between March and June 2007, which shows this defrosting to sort of increase, all these dark defrosting spots to increase as the season progresses from spring to summer. And such is the case in the Arrakis dune field as well. This is a region in the northern hemisphere, which again, in the local spring and summer seasons, the defrosting spots sort of keep on increasing. There's one such process that's only seen in the northern hemisphere as compared to the southern hemisphere. It's not solely frost dominant as the southern hemisphere is. It's sort of like a combination of both mass wasting, like landslide sort of activity, and frost activity, something we call as polar avalanches. Now, what basically happens here is that, as I had mentioned before, the North Pole is sort of differently made as compared to the South Pole, right? The North Pole is made up of all these layered deposits, which are basically alternate layers of dust and water ice that have been deposited over multiple time periods, about millions of years ago. Now, one thing to note is that this sort of sedimentary structure that's being formed near the poles is in fact very high. These cliffs are almost 500 meters or a kilometer high, almost. And often these slopes are greater than 50 degrees or so. So what happens is that CO2 frost gets deposited on the surface during the local winter. And as it gets sublimated during the local summer or spring seasons, this destabilizes this entire slope. So what happens is the ice blocks, especially at the boundary region near the rim of the slope, they tumble down this entire cliff. And then because these scarps are steep, when they come down, this avalanche sort of like kicks up dust clouds at the base of the entire scarp. Now, it is still unclear if this is the seasonal frost indeed is triggering the avalanches, but because the timing of this activity corresponds to the seasonality in which we should expect springtime CO2 frost sublimation, this seems to be the most likely scenario to be causing this change. This kind of similar to the snow avalanches that we see on Earth, but the only difference is that it's not actually caused by CO2 frost on Earth as it is on Mars. Now, the really cool part about this particular change is that we were very fortunate that we could catch this activity literally in action from the HiRISE camera on board the Mars Reconnaissance Orbiter. In fact, this HiRISE image, it was taken very early in the primary science phase of the mission, wherein we could identify at least 4 simultaneous polar avalanches that were taking place at the same time, almost in real time when the instrument was actually over this region. This is another later image that was taken just in Mars year 35. We can see a nice like dense snow avalanche that was seen here. So this is pretty interesting as to how dead we thought the Martian poles were initially. Let's just now move down to some of the mid-latitude processes that are occurring, which are less governed by ice as much as the polar processes, but are more governed by these mass wasting sort of like phenomena that we see on slopes. Now, because they occur on slopes, I've just given a generic term for most of them called as slope processes. They're basically classified into 3 major types that we see on Mars. We have the gully formations, something that I've been studying towards my PhD thesis. We have something called as a recurring slope lineae and something like dark slope streaks. Now, out of the 3, in fact, gullies, we do have analogs on Earth, which makes it even more interesting as to how they could have formed on Mars, which I will be talking about in the next slide, actually. Let's just start with each of these features one by one and see what's exactly going on here. Now, what are these gullies, essentially? They're basically simple erosional features, and they're made up of 3 distinct parts. Basically an alcove, which basically carves out the sediment from the bedrock. we have a channel that transports the sediment from the rim or the upslope region to the downslope region. And we have a depositional apron, which basically consists of the deposits that have been transported downslope. Now, these were first identified by Martian and Eject in 2000 from the Mars Global Surveyor sort of spacecraft. I think from the Mars Observer camera, to be even more precise. Now, before that, we didn't know that gullies were present on Mars, apparently, because we didn't have high-resolution data sets at all in the first place. Now, one very interesting thing that we find about gullies on Mars is that it's only found in the mid-latitude regions, about 30 degrees to roughly about 65 to 70 degrees. We don't see a lot of them above 70 degrees. They're very rare. And they're usually active during the local winters when the amount of CO2 frost starts getting lower and lower, and there's some sort of like sublimation going on. And this, they may occur in different settings, because all you need for a gully to occur is a slope, right? They can occur in impact crater slopes. They can occur in slopes of large channel systems that you have. But for some reason, impact crater slopes have been the most preferred setting that we see on Mars. This could probably be because the slopes are much more higher as compared to other channel systems. But this is still an understanding or an overview that we have. We don't still actually know why this is the case. As I mentioned before, the cool part is that, yes, we do have analogs on Earth. Gullies do form on Earth. One really good example is that, now this image on the left side of the screen, this is actually a set of gullies at Thomas Lee Inlet. There's a region on Devon Island in the Canadian High Arctic. And this is a set of gullies, type of gullies rather, called polar pit gullies in the northern hemisphere of Mars. I think this is in the northern hemisphere of Mars. So when you compare these two, they look so very similar, right? As compared to their morphology and how they are sort of like their channel systems and everything. So when they were first identified, everybody was like, yeah, water is probably the driving force behind Martian gully formation. But one thing to note is that these gullies are actually geologically very, very young. How do we know that? That's because these features almost superpose every other sort of like geologic feature that we see on the surface. So these gullies have definitely been formed probably within the last 10 to 15 million years or so, not older than that, geologically speaking. So they were formed at a situation when water was not technically stable at the surface. So that makes it even more interesting, because most of the gullies that we know on Earth have been formed majorly by meltwater or by flowing overland flow or something like that. So that caused many other people to propose so many other mechanisms as to how these gullies could have formed in the first place. We had models proposing dry granular flows, something similar to like snow avalanches that you have in Svalbard or somewhere in the polar regions. Also, frost sublimation driven mass wasting processes were proposed. Currently, amongst the scientific community, we all agree that CO2 frost sublimation could be the most likely scenario for at least present day surface changes. But what actually caused initial formation of these features, we still don't really know. So it's still a huge question that's there in the gully community. And that is a prime picture of what I am exploring towards my PhD thesis as well. But just to give you a perspective of how this study has actually improved over time, right from the first gully that was identified in 2000 in Martian and Eject's paper, currently almost 4,500 gully sites have been identified on Mars from various global surveys that have been conducted from different remote sensing spacecrafts. The latest one being conducted in 2015 by Harrison et al. In 2015. Yeah. Out of these, at least in 110 sites, which are represented by these small yellow dots in this entire map, they have been reported to have very recent activity. So this makes it even more interesting as to, okay, this is a very, very active process that's going on the surface at present day. it's imperative that we know what's exactly going on and what's causing this process to actually occur in the first place. Now, apart from gullies, there are two other very interesting processes that take place in the mid-latitudes, especially on slopes. Something called as a dark slope streak. Now, this is not actually seen on Earth at all, apparently. This sort of analogous to Mars, and this sort of baffled scientists when they first found this from the Mars Observer camera on the Mars Global Surveyor. Now, we have both bright and dark slope streak formations on these slopes. While the mechanism of formation or how they are triggered is still heavily debated, they're most commonly believed to form by downslope movement of extremely fine sand in an almost fluid-like manner, very similar to a snow avalanche on Earth. Now, as it moves down, it exposes some darker underlying material that's already there on the slope. The darker slope streaks are supposedly younger as compared to the brighter slope streaks, which are essentially thought of as maybe older dark slope streaks, which are just covered by dust over time. However, there has been some research going on about impacts being a potential trigger for these slope streaks. This is a very nice high-rise image that was taken not very long ago, wherein a very recent fresh impact crater actually triggered a large slope streak to form downslope, actually. This doesn't clearly give a nice picture of the elevation aspect, but the lower elevation is towards the top side of the image here. So such a small impact, basically what happened is that the impact sent in shock waves into the surface, and that caused these finer material to sort of like segregate and go downslope, causing formation of these features on the surface. Yet another feature that we see in the mid-latitude regions are these nice little features called as recurring slope lineae. At first glance, they may look like dark slope streaks, but the major difference between this and dark slope streaks is that the time period wherein a dark streak fades into a lighter streak is of the order of 3 to 5 Mars years or so, probably about 10 Earth years. However, these recurring slope lineae, as the name suggests, they recur every year. So they lengthen, they fade, and then they reappear. So when they were first identified, the first proposed explanation was probably this is because of some liquid flow that's occurring on the surface. However, because we didn't find any hydrated mineral signatures or any sort of fluid associations along these deposit regions, our understanding has definitely shifted from the first identification. And currently, we think these are essentially dry processes that are going on. Now, both dark slope streaks and recurring slope lineae, unlike gullies, do not have analogs on Earth. So this makes it very, very difficult for us to sort of understand what exactly is triggering these slope lineae to actually form in the first place. And this is still a large study that's going on amongst the scientific community across various universities in collaboration with the HiRISE and the CASIS instrument teams. Now, moving over to the equatorial sort of region now. The equatorial region, as I mentioned before, is dominated by processes that are governed by wind. Now, wind occurs on Earth as well. So most of these processes have analogs on Earth. Now, very similar to the alien landforms on Earth, we have these dune landforms on Mars as well. We have different types of dunes. We have these Barcan dunes. We have linear sort of like ridges of these dunes called as transverse alien ridges. And all of them have seen reported activity. The only difference between Martian dunes and the Earth dunes is that the movement is much, much more slower. Now, this we think is because Mars has a much lower gravity, so a lot of sand is actually getting deposited there, and the elevation of all these dunes is very, very high as compared to the Earth's dunes. So this makes it even more difficult because we need a much higher wind velocity to sort of move and saltate these dune grains from one place to another to cause any appreciable change in the dune movement that can be recognized by any of our instruments that we have on a spacecraft that are currently orbiting Mars. So any appreciable change, like say a movement of about 2 meters or 3 meters or so, takes at least one Mars year at the minimum. Now, there are some very interesting alien features that take place on Mars as well. Something called as a dust devil. These are essentially rotating columns of dust, which essentially form when the near surface air temperatures increase during local spring or summer. So what happens is when the air temperature increases, causes some sort of a low pressure air pocket or a vacuum form there in the near surface atmosphere. So it pulls dust and forms some sort of a tornado and moves around the surface. Now, this is very similar to Earth as well. We do have dust devils on Earth too, especially when conditions become very hard. This is a nice dust devil that was imaged by the University of Arizona team in the desert in Arizona. Now, however, on Earth, many dust devils are usually small and weak, just because of the greater gravity, of course, of Earth, and they're often less than 3 to 5 feet in diameter. And the maximum wind speeds don't exceed 45 miles per hour or 70 kilometers per hour. However, on Mars, that's not the case because the gravity is so low. They rise almost up to around 10 times as high as terrestrial dust devils. And they could be almost 50 times as wide as the ones that we have on Earth. So definitely the larger ones will pose a huge threat to all terrestrial technology that we send on Mars, and also to astronauts if we do have a landed mission on the surface. Now, how do we understand or how do we know how they about their wind speeds and stuff? Is that these dust devils basically leave tracks behind them as they move from one place to another. And this is a Cassis image that was taken of a large number of dust devil tracks in a dune field in Syrtis Major Planum. It's a volcanic field near the equatorial region of Mars. This is just west of where the Jezero craters landed. I mean, it's not very close, but in that unit region at least. So yeah, these have been recorded by various visible and NIR imagers on various spacecrafts, and they are constantly studied. This also forms a part of my own study as well, to understand about their movement and what actually happens in the first place. Now, those dust devils were very localized in one region or another, right? Now, sometimes once every 3 to 5 Mars years, we have something called as a global dust storm that almost envelops the entire planet. There's a thick cover of dust that's formed in the lower atmosphere, which virtually blocks almost all of the sunlight that reaches the surface. This apparently was the cause for Opportunity's mission end, because Opportunity was driven by solar power, and because the global dust storm in Mars year 34 in 2018 completely covered the entire region there. Some of the Mastcam images that were retrieved by the Opportunity rover, they showed very, very dark skies, just representing that there was absolutely no sunlight that was penetrating through this dust layer. So during these dust storms, basically, the dust devil activity actually increases manifold. So it causes this formation of something we call as dust towers. This is just a fancy name of a concentrated cloud of dust that's basically lofted dozens of miles above the surface of Mars. Now, what happens is these dust towers, because they're essentially a low pressure air pocket, they act as an elevator carrying all other materials that are there on the surface up to the top of the atmosphere. That's why they're almost always accompanied by water ice clouds. Typically, maybe the water ice frost that's present at the surface is lifted up by these dust towers, and it's sort of like vaporized at the top of the atmosphere. Seeing this Marcy image that was taken during the Mars year 28 dust storm, scientists actually think that this could have been the reason why Mars's water disappeared over billions of years ago, by formation of these dust towers and these large elevator sort of like features there. Now, we have been fortunate to be able to observe at least 3 global-wide dust storms till now from remote sensing spacecrafts. one in Marcio 25 from the MJS spacecraft. We had a couple of them that were observed by the Mars Global Surveyor, as well as the Mars Reconnaissance Orbiter in Marcio 28 and Marcio 34. Now, this sort of like summarizes almost most of the active processes that we see on the surface. Again, one thing we could have understood from this is that Aeolian processes and probably some amount of slow processes do have some analogs on Earth, but most of the CO2 frost dependent phenomena do not have any analogs on Earth. So most of our understanding of what actually happens on the surface is based off on all these remote sensing images that we get from various spacecrafts that we launch in Martian orbit. So for change detection aspect, the Mars Reconnaissance Orbiter as well as the Trace Gas Orbiter have been instrumental in helping us identify, track, and monitor all these different kinds of changes that we do see on the surface. Typically on the Mars Reconnaissance Orbiter, we use these two visible and NIR remote sensing imagers, namely the HiRISE or the High Resolution Imaging Science Experiment and the context camera. Now, one thing to note is that the Mars Reconnaissance Orbiter is in something we call as a sun-synchronous orbit. What that means is that multiple images of the same region taken from this instrument or from each instrument are taken at the same local time each acquisition. So currently, both HiRISE and CTX are at a 3:30 p.m. local time orbit at present. The High Resolution Imaging Science Experiment actually is able to resolve features as small as 25 centimeter on the surface. And the context camera gives us a much more broader perspective, roughly about 6 meters per pixel. Now, both of them are essentially panchromatic imagers, which means that they're essentially single band images, but better spatial resolution. Now, HiRISE does have a small, very narrow color strip with a width of about 1.2 kilometers, which images in 3 specific wavelengths: the blue-green channel, you have the red channel, and the NIR channel, just to give a color aspect to what's actually going on there. However, CASIS is basically a color instrument predominantly as compared to HiRISE and CTX. The ExoMars Trace Gas Orbiter, however, is not in a sun-synchronous orbit. So this can be both of an advantage and a disadvantage. Because an advantage basically, because this can uniquely image Mars at multiple times of day. So we can not only identify seasonal processes that are occurring on the surface, but also identify and track diurnal processes, something that might be changing in the local day and local night. So that can be tracked and monitored from the color and stereo surface imaging system. Now, CASIS, on the other hand, has a much wider color swath. It gives us full width color images up to about 9.5 kilometers. And it also has an additional IR channel, which also allows us to compositionally define and constrain all of these changes that we see on the surface. Now, we do have other operational VNIR images on Martian orbit currently. This is just a quick shout out to that, but we're not dominantly using these imagers for change detection as of now, but surely they could be used in the future. We have the HRSC on the Mars Express, which is almost one of the long-standing spacecrafts that has been sent by the European Space Agency. We also have the Mars Color Camera on board the Mangalyaan 1, for which I did work briefly in an extended project now. We have the Emirates Exploration Imager, which was just launched earlier this year by the HOPE spacecraft from the United Arab Emirates. And we also have China's high-resolution imaging camera on board the Tianwen 1 mission. Now, because HiRISE and CTX, as I mentioned before, are on a sun-synchronous orbit, most of the change detection that takes place with these two images are essentially qualitative in nature. What that means is that we just, because there's only one variable here, the time of the day is almost the same between images. The only variable here is the illumination that's there on the surface. And that usually depends on which season you're looking at you're taking the image in from Martian orbit. Now, that's one reason why qualitative techniques can basically be applied. You can just have a pre-change image, you can have a post-change image, and manually compare these two images to see if anything has changed between certain time periods. Now, that being said, quantitative analysis can also be done, but only if similar geometry is maintained and we have some sort of an elevation data set to go along with it, something we call as a digital terrain model. Now, this is just one example of a quantitative study that was done by Chonaki et al. In 2015. They tried to constrain the alien activity at Endeavour crater. This dune field is one among the most active dune fields on Mars. This is very near the region where the Opportunity rover actually visited the rim of this crater. And they calculated the migration rate to be roughly about 4 to 12 meters per Mars year. So you can clearly understand how slow this migration actually occurs in the Martian surface. Now, unlike HiRISE or CTX, with CASIS, you cannot really do qualitative change detection. This is because, as I had mentioned before, CASIS is not in a sun-centric orbit. So almost always, successive images taken over a specific region are never at the same local time. So what we do is something that I have been working towards in my PhD thesis, is to develop techniques and mechanisms to use CASIS for change detection through the spectral aspect of the spectral advantage that CASIS provides. Now, CASIS is a relatively new orbiter. It has just started imaging from 2018. So to supplement these CASIS images, we also simulate CASIS-like products from from merging the spectral details from CRISM and the spatial details from CTX or HiRISE, both on the Mars Reconnaissance Orbiter, which was launched in 2006. It was launched in 2005, but it started imaging in 2006. So we have like a whole array of both simulated CASIS and actual CASIS images right from 2006, so that we can establish a very robust regular change detection scheme right from the time MRO started imaging. This is just a small snapshot of how a simulated CASIS image or even an actual CASIS image would look like. You can see it has such a wide color swath as compared to the HiRISE color strip, as I mentioned, which is just about 1.2 kilometers. So we decided, hey, CASIS has an additional spectral channel. It can be used for compositional studies, so why not take the best advantage of that? So towards my own PhD thesis, I tried to develop two methods in which we can do such analysis for change detection. Now, this is based on a very simple logic. Now, we know that most of Mars basically looks reddish in color, right? That's because of the ferric iron oxide that's present on the surface, and majorly because of dust that's present there. Our logic was any new change that's actually occurring on the surface would definitely overlay this ferric sort of region in the background, right? And thus, its spectral behavior would definitely be different from the surrounding ferric region. And this would be a little less ferric, or probably shift more towards an unoxidized ferrous state. Now, apparently, both ferric and ferrous minerals absorb different wavelengths of light in the electromagnetic spectrum. Ferric minerals absorb 550 nanometers wavelength, and the ferrous minerals absorb 1000 nanometer wavelength, which is reflected in their electromagnetic spectrum, or the reflectance spectrum of these two minerals. So we basically use that to our advantage, and we developed spectral band ratios to identify and confirm these newer changes that we see on the surface. So the pan over NIR ratio, it basically is trying to tease out the 1000 nanometer absorption of ferrous minerals, and all the three other band ratios here, the pan blue, the red pan, and the NIR blue, teases out the ferric nature. It's more sensitive to ferric minerals on the surface. So for any new change that's occurring, this just a combination of two simulated CASIS images that was taken in Mars year 31 and Mars year 29 and Mars year 30, apparently. And you can see where the new changes occurred. There's a bright blue coloration that we see that is shown by this arrow, right? So there's a new gully change that's occurring between these two time periods. So we try to test our techniques out here, and as we envisioned, our technique did help identify this change really better, or even confirm that this change is actually real. Because wherever these new changes occurred, the ferrous ratios increase and all the ferric ratios substantially decrease. This is also reflected in the reflectance spectra of both of these regions that we see from another technique that we developed called as an in-scene spectral analysis technique, wherein what we basically do is that we take a region inside this sort of change area, and we take a region outside this change area, maintaining the same slope so that we don't introduce any topographic bias when we're doing this analysis. So this represents the pre-change image, and this represents the post-change image. So in the pre-change image, because there's literally no change occurring here, all of the region is ferric. So it has this clear absorption short of the 550 nanometer region. However, in the post-change image, inside the change region, which is represented by this red spectra, the spectral limb between the red channel and the NIR channel of Cassis actually dips more towards the 1000 nanometer range, which sort of indicates that, hey, there might be some ferrous mineral that's present here. So this sort of confirms our analysis or our understanding that most of these newer changes are essentially ferrous, or they are rich in ferrous materials, pretty much. This was also validated by other sites as well. We tested it out on a bunch of slope streaks that was identified by a new Cassis image. It actually, you can see the time difference here. It almost took 4 Mars years for actually these slope streaks to form in the first place. And here again, at the region where these slope streaks are formed, the ferrous ratio increases and all of the 3 ferric ratios decrease. And similar behavior is actually seen in this in-scene spectral analysis technique as well. So currently what we're doing right now is we are testing both these techniques as an alternative for change detection on a variety of other surface processes that we have identified that are there on the Martian surface, right? There are a plethora of processes that I've shown you before. So we're testing it out on all of them, and we are developing a robust method for TGO. And this is very critical because the mass reconnaissance orbiter is an aging instrument. So it could be that there might be some challenges in the way we do change detection from the mass reconnaissance orbiter, but that should not impair our continuous studies of these active surface processes, because that's very critical in case we do have landed missions in the future. So almost to end here, the current developments and what are the pathways forward that we have for active process studies on Mars is that now, because we see Cassis-based techniques, at least the spectral Cassis-based techniques, are found to be really helpful for identifying and tracking these changes. Not only that, but also telling us something about the composition of these deposits itself, which we can trace it back to how or what could have affected formation of these features in the first place. So this will definitely guide future Cassis-based monitoring campaigns for all active surface processes in the near future. And definitely for most aeolian processes and at least gullies, as I mentioned, we do have a lot of Earth-based analog sites, which we should look at a bit more keenly to better understand how these features could have formed in the first place. Like, for example, this figure on the right side of the screen, these are a set of gullies at the Houghton impact structure that I'm actually currently investigating as part of my PhD thesis. These are formed in the Canadian High Arctic, in an island called as Devon Island in the Nunavut region. Now, because the area or the temperature or the environment in which these gullies form is kind of like a semi-arid cold desert, very similar to what Mars is in the present day. And because Martian gullies are geologically relatively young. So it's very interesting to see what results we might obtain from field studies of field and morphologic studies of the gullies here. And apart from that, there are also many alien process analog sites on Earth. This is just one example where scientists have been regularly going to and trying to do analog studies here. The Namib Desert dunes in southern Africa, they very much resemble how Martian dunes sort of form and activate in present day. Not only for Mars-based studies or even better understanding Earth-based studies, understanding what's actually occurring on the Martian surface has profound implications for all future space exploration in the entire solar system for that matter. This is because alien surface processes and sublimation-driven geomorphic phenomena are not just restricted to Mars and Earth alone. We have dune-like features. We have actually seen dune-like features from various images on Pluto, even the comet 67P, and radar images of Titan that was taken by Cassini. Not only that, these sublimation sort of pits that we see on Mars, sort of something similar to like the Swiss cheese terrain. We also see something very similar in messenger data in Mercury, and also small pit-like structures on Pluto, which was imaged by the New Horizons spacecraft. Now, gullies are not only seen on Mars, they have also been observed on Mercury as well, very recently from the messenger spacecraft. And because we do have the Bepi-Colombo that's en route to Mercury in present day, that will provide us with a plethora of data to better understand these gully activity that could have that is being formed in the Mercurian surface. Now, gully features are also seen in Vesta, the asteroid in our solar system. Now, because Mars has sort of like established that simple geologic features like gullies or slope streaks or even sublimation pits can be formed by exotic means. By exotic, I mean something that we are not accustomed to seeing on Earth. Mars sort of acts like a natural laboratory for comparative planetology studies for surface processes across our entire solar system. Now, last but not the least, better understanding Mars's surface processes definitely will give us a better knowledge of current and past environmental variables, which is absolutely critical for human spaceflight programs to Mars, which is a definite in the near future, especially so that we can have robust and better missions to Mars in the future. Thanks so much for your patience. I'll be happy to answer any questions now. Thank you.
Thank you so much, Vidhya, for sharing your research and for giving us insights into all of this amazing activity on Mars. We're going over now to our outreach coordinator, Shaheen Dashkian. I've heard that there are a number of questions from our YouTube audience. Shaheen?
Thank you, Denise. Vidhya, I hope you're ready for this. There's a lot of good questions that have come through the chat. So I'm just going to shoot them all at you and see how it goes.
Sure.
So the first question that we have is from Nerd Incognito Sue. And they would like to know, it's a really good question actually, what fascinates you most about Mars?
Apparently, much more recently, I've been able to appreciate how Mars is not as similar to Earth in the first place, especially with the planet wobbling and the obliquity variations and all those things. To pick an active surface process, I would say because I am studying gullies and slope processes, I have some sort of a favor towards that. They are very intriguing features because they are formed at a time period when we don't think water should have existed on the surface in present day, but however, they look so much similar to all these fluvial features that we see on Earth, right? So this is very intriguing and sort of makes us, it puzzles us as to what's actually causing these features to form in the first place. And every day we get a new image of all these features, it poses a new question in itself, and that's what makes our understanding or our research of these features even more exciting and challenging for that matter.
Thanks for that. This next one is a That was a really good question. If it was possible, what planet would you visit and why?
Well, again, I would be biased here because I've been most of my work has been for Mars and the Moon. I'm heavily biased towards Mars because I've been studying a lot of that. However, if Mars is not viable, I would definitely love to visit the Moon as well. Simply because although it's our closest neighbor with respect to the solar system bodies as such, there's a lot that we don't know about the Moon as well, as to, like, we have impact melts, we have lava flows, we have so many other processes that has occurred on the lunar surface, and it's again intriguing and challenging. So my first preference would definitely be Mars, because I'm heavily biased towards that, but I wouldn't mind visiting the Moon as well.
Great. The next one is from our very own Rask Toronto. If you were a consultant for human missions to Mars, what geological area and feature would you recommend investigating first?
I personally would recommend visiting an impact crater that has well-preserved gully features. There's a very it's not a bias that's actually governing this answer. It's essentially because most of the frost-related phenomena, we sort of have some kind of hang of as to how they are forming in the first place. But for slow processes, it's still a huge debate with respect to whether they're formed by a wet process or a dry process. I would agree. I mean, for all the three slope processes in particular, we have the dark slope streaks, we have recurring slope lineae, we have gullies as well, which we don't know if it's dry or wet. So I would presume that's one of the key areas where we do need human landing missions there, especially because once we get down, once we have geological samples in hand, then we can gain a better idea of as to what's actually happening there, and get a better idea of the basic geologic history of that region in itself.
Thank you, Vidya. Got another great question from Sue. They're asking, can you recommend a good book where I can learn more on this topic, or even a website?
Oh yeah, sure. I recently read a book. I mean, it's an academic book rather, but it's very well written, apparently. It's a book called Dynamic Mars. It was edited by Richard Soar and Susan Conway. I think there was one other editor there. I seem to forget their name. But it's a fantastic book for all these active surface processes. It clearly gives you a breakup of, okay, why do we see what we see on Mars? And this gives you sort of like an overview of like what could be the case if Mars was not in an orientation as it is right now. Yeah, it's a very nice book. I would recommend that if one was interested in active surface processes.
Awesome. And did you say it was called the Dynamic Mars?
Yep, it is. Dynamic Mars.
Great. I'll make sure to put that in the chat for our viewers. We have another question from Barry. Given all that we've learned about Mars's processes, what changes and modifications have been made to recent missions to help ensure the operation and long-term survival of the landers and rovers?
So, yes, apart from Phoenix, we don't really have I mean, after Phoenix, we didn't really have a lander or a rover that has visited the polar regions, or the north, or the high latitude regions at least, of Mars. I would say the Zhurong rover, which has landed, China's Zhurong rover, I think that has landed in Utopia Planitia, which is the highest latitude amongst the currently operational rovers that we have right now. And that uses an RTG instead of a solar sort of like powered array to power up its instruments. That's something we definitely have learned, that solar power cannot be used at high latitudes at all, because it becomes extremely cold and critical in these high latitude regions. One thing definitely would be to make the systems much more stronger and robust, such that they can withstand heavy masses of frost or ice deposition on the surface. But apart from that, I think we don't have any planned missions yet. So if there are, definitely solar power would be a no-go. That's what we have learned from at least Phoenix, for that matter.
All right. Here's another good one from Barry. If you were in charge of choosing the next Mars mission, what would its focus be?
Okay, wow. So I personally am a spectroscopist. So I would really, really love another imaging spectrometer on Mars, at least with a finer resolution as compared to what we have. I think currently we do have XRISM operational on the Mars Reconnaissance Orbiter, but because there were some issues with its IR portion of the detector, we are not able to get the long wave portion of the data anymore from 2012. So we really, really need an imaging spectrometer on Mars, and that definitely should be the next orbiter, at least, that should go to the Martian area. Now, we do have an ExoMars rover as well that's coming up next year, for which CASIS is actually providing imaging support because it's part of the same sort of joint paired mission from ESA. So that's something interesting as well. It's going to explore a really nice, a diverse mineralogically diverse terrain in Oxyaplanum. So that's something to look forward to. And yeah, we will be getting some exciting results soon in that region.
Great. Staying on that same topic, Chris Vaughn would like to know, using current instruments in orbit, can you take spectra of the surface to measure water concentrations in the gullies and elsewhere?
So currently, amongst most of the spectrometers that are active right now, we the best spectral resolution, at least, we have only the XRISM shortwave instrument that's currently operational. With XRISM, it's going to be a bit difficult, I would say. We can't do quantitative studies, essentially because most of the water ice absorption features are in the IR portion of the spectrum. The XRISM shortwave range of the spectrum only extends to about 1 micron. Now, there is a water absorption feature which is very weak in the 1,000 micrometer sort of range, which CASIS actually can pick it up. We did try, we had written an abstract highlighting this in the last Lunar and Planetary Science Conference, of which, I mean, it was done by our group here at Western, apparently, that we somehow tried to pick up that 1,000 nanometer absorption a bit more better than XRISM did, because the XRISM instrument did not extend fully into the 1,000 nanometer absorption range. But I mean, we can still, I think we can still separate very, very qualitatively if ice is present or not present. But it's going to be very, very challenging with the current instrumentation that we have on orbit to conclusively tell how much of ice is present and to what extent. But definitely qualitatively it is possible.
Awesome. And finally, two more great questions from Sue again. Sure. The first one is, do you think there will be someday like commercial flights or space tourism to Mars in the same way we just saw with Bezos and Branson going to space?
Well, I definitely think, and I hope so. But surely Mars wouldn't be the first stepping stone. It would take at least a couple of decades before we actually reach Mars, in my perspective. Surely commercial space flight, we have been able to achieve at least Earth's orbit. Not exactly Earth's orbit, at least a lower Earth sort of orbit. But the first ideology would be to better explore the moon, because it's much more closer as compared to the Earth. The only reason why it's going to be challenging on Mars is because when you do have a very long travel time, because even when Mars and Earth are at its closest, you still need about 6 to 8 months to travel. So I think that's going to be the key factor as to how astronauts can sort of like maintain their cool and composure as they travel, as they are in this travel phase. And the moon is kind of slightly safer as compared to Mars, especially with respect to active surface processes going on. Like we need to be aware of, there's still a lot of science research that has to be done before we can say Mars is actually safe for humans to land at the present day. But this is surely a possibility in the next couple of decades, I would presume.
Wonderful. And finally, we have our last question from Sue. Now, this one's kind of a general question, but perhaps you can answer this through the lens of someone who views Mars quite often. And she's asking, what telescope would you recommend for a beginner to astronomy?
Oh, geez. I am not an astronomical person, so I am not completely aware of that. So yeah, I really wouldn't want to give a wrong answer down here. So yeah, I'm more of a satellite remote sensing person. So I'm sorry I couldn't answer that, but that's a wonderful question. Mars is actually visible to the naked eye as well. So sure.
Yeah, and you know what? Perhaps afterwards we will kind of talk about a pretty cool telescope that we know all about coming up. So Denise is going to talk a little bit about that in a few minutes.
That's awesome.
And I think that's it for all our questions today, Vidya. Thank you so much for answering all of them.
Awesome. They were very wonderful questions.
They were, yeah.
Thank you, Shaheen, for relaying all of these great questions from our audience. And thank you so much, Vidya, for answering them in so much detail. I think we've all learned a lot tonight.